This is that. This is the last page of that very long packet I gave you. We've got a massless. Let's see, get this massless, frictionless pulley, and a frictionless ramp. And we want to know the acceleration of the red box up the ramp. Now, it's probably not obvious to a lot of people that this box will actually go up the ramp because a lot of people think since we've got a smaller box, that won't happen. The bigger box is on the ramp. But remember, the bigger box is acting on the ramp, so it's experiencing a force that's equal not to the weight but to the parallel component. So if the box is going up the ramp, we'll call this direction positive, this direction negative, and let's find the acceleration of the red box up the ramp. So the only way to find acceleration is, well, let's do it this way. F net equals ma. It's Newton's second law. And what are the positive forces? Little mg. And the negative forces, the forces in the opposite direction, would be big mg sine theta. And what do those two forces accelerate? Both masses. Oops, let's get a little bit cleaner there. The big mass and the little mass are both accelerated. So now we just solve. Take the mg minus the big mg sine theta and divide both sides by little m plus big M. You see, we just divided it by that number there, for those sets of variables, and I've got it. There's the acceleration. Now the masses move together with a single acceleration. I mean, it'd be ridiculous any other way, right? They have both accelerate. They both will have the same acceleration. Prop this up a little bit better here. Okay. When does the acceleration equal 0? So let's write the equation again. Mg minus big mg sine theta, the parallel component. What does it accelerate? Both masses. So when does a equal 0? Well, a equals 0 when this numerator equals 0. When does that happen? When mg is equal to mg sine theta, cross out the g's. So when little m equals big M sine theta, the acceleration will be 0. Under what circumstances will the large box accelerate down the ramp? Well, since we called up the ramp positive, down the ramp would be negative when the acceleration is negative. So let's look at our equation again. Let's look at the equation again, which is right here. So when is the acceleration negative? When the numerator, right here, when the numerator is negative, then the acceleration is negative. If you have two numbers, remember a small number minus a big number gives you a negative number, like 6 minus 7 or 10 minus 15. Small number minus big number gives you a negative number. So when mg is less than, mg sine theta, then a would be a negative number. A is, well, it's right here. A is negative. Okay, let's recap what we did. We're told this red box is going up the ramp. They called it big M, so I labeled it big M. We're calling up the ramp positive. This whole direction is positive. And that makes mg, this force is mg. It is a positive force. It's going in our positive direction. Mg sine theta is going in a negative direction. What do those two forces, those battling forces, accelerate? Both big M and little m. Plugging into Newton's equation, we get this. When we divide both sides of the equation by this, and we get a alone. That's an m, not a mu. It's a big M. Both masses move together with a single acceleration. And I guess we took it over here. We factored out. Let me see what happened here. Oh, no. Okay, good. All right, back over here. When does a equal 0? A equals 0 when this numerator, this fraction equals 0. And that's only true when these two terms on the top equal each other. So when little mg equals big MG sine theta, I cross out the g's, and that is when little m equals m times sine theta, we know that there'll be no acceleration. Either it will be at rest or with constant velocity. Under what circumstances will the large box accelerate down the ramp? Which means in our system, down the ramp is negative. So the acceleration is negative when the first term in my fraction is small and the second term in my fraction is big. And that is it.